Welcome to Lecture 8 of MCS 507 on Mathematical, Statistical and Scientific Software. We are at the end of week 3, a week that has as theme arithmetic and wrapping. So we conclude this week with some more involved programming projects, but the purpose is also to introduce more features of Python. So the title of the lecture is Overloading and Extending, where the overloading refers to the operator overloading, which will be illustrated with differentiation. At the beginning of the week, we wrapped up an external program. We made it available in a Python session via plain calling the executable, and that was very good to illustrate the file manipulation system in Python. Now for arithmetic, this is not really that appropriate, and I will indicate in this second part how to import C code. In a way, as far as this course goes, if you have no familiarity with C, then this may be too technical. It's important then that you mainly know that it exists, and also why Python can still be very effective if all the computational, if the most computationally intensive operations happen in compiled code, then it's perfectly fine to use Python. Towards the end, I will indicate some more heavy programming and actually very useful programming projects, which are optional here. Okay. So a reference that I could have listed also last time with the interval arithmetic was the textbook of Neumeier, who's an expert on interval arithmetic, but who wrote a nice introductory book to numerical analysis, and one could consider numerical analysis from the perspective of rigorous computing. So what I'm using this book for is a very nice description, a very short description on how to work with differential numbers, and actually to explore what is called the forward mode of algorithmic differentiation. So algorithmic differentiation is a big topic, and one could spend an entire course on this. But I hope that with this small introduction, you get somehow the flavor of the field. So what is a differential number? A differential number consists of two doubles. It is the value of a function, and the second element in the tuple is the evaluated derivative. So the idea is, as you are computing, if you do the addition of two numbers, if you are doing any operation, you would also apply the derivative rules while you are doing this. So if the elementary operations, the derivative operations, are actually defined, then simultaneously by doing the evaluation, you could also compute its derivative. You can see that this is very useful in the context of optimization. Alright, so here are the rules. So they are defined on tuples, where the notation suggests that the second element in the tuple is the derivative of the first element. And here we assume that everything depends on the same independent single variable. So there's only one variable there. So we never need to essentially write. So this can all be done very numerically. Okay. Or numerically, Python has a dynamic typing system, so it can work for also symbols as long as the derivatives themselves on the symbols are defined. Okay, so we have the basic elementary operations on the addition, the subtraction, the multiplication, and the division. And also we have the extra rules on a constant, so how a constant is represented and how we represent an independent variable. So we actually work symbolically with this independent variable, and we build expressions and at the same time evaluate them. Here is an example. So if we have the function f, we can all compute its derivatives, but with the rules we can compute the value of the derivative without having to construct the formula for the derivative. So this works with the differential number arithmetic as explained here. So we want to evaluate the function at 3. So we represent the differential number at 3, 1. So, and we do our arithmetic. So we subtract 2 from it, and then we multiply with 3 added to it. So you see the derivatives on the applications rules. So the constant 1 is represented as 1, 0. So we apply the rules on the subtraction, and then also the rules on the multiplication and the division. So here you see how it gets interesting, how we at the same time, without having to compute extra formulas, we compute the derivative by a rule-based manner of working. Now, if you had to do this by hand, it looks interesting to do this once, and it's useful to do it once as an illustrative example, but you don't really want to do this all the time. So we're going to define code for this. So in a way, this is again, this is an extension on the lecture on object-oriented programming in Python. So we will define the class differential numbers, the class differential number. So when we define a class, we start with the constructor. So for the constructor, we allow that we define just the differential number on a constant. So the prime part, the xp equals 1. So what the constructor does, it defines the data attributes for any instance of the class. Everything will be done with floating point arithmetic. So I said that we could do this symbolically, but here we are interested in purely numerical results. Okay, so immediately after the constructor, we define the string representation, and here every differential number will just be returned as the string representation of the tuple. So we take the two data attributes, which are called val and der, and we put them in a tuple and apply the string method that is defined on a tuple. So in the object-oriented terminology, we say that we override the built-in string method, but now for an object of our class. All right, so now comes here the main point. If you want to do this kind of in a very nice way in Python, you would like to write the rule just as the addition symbol. So the addition symbol can be redefined or overridden in the proper technology by the add operator. So an add is built in, so therefore the double underscores before and after the name. So we had the self, and if there is a self, there is also an other. And the other is used to indicate the other argument in an operation that takes two operands. So the plus operator generally always has two operands, the first and the second. The first is used for the self, and then the other is the second operand. So what do? We just apply the rule here. The rule is codified, and we return a new object. So the return differential number makes that we apply the constructor again. So we do not modify nor the self nor the other. A proper add never modifies the operands, but we return a new object, a new instance of that class differential number. Okay, what if the other is actually not a differential number? Then we can check whether the other is actually an instance of float or not. So this makes a better rule. So you may want to write x plus 2, where we want to define where we want to check first whether our other is an instance of float. So is instance also works on any type. Python is object-oriented and has an elaborate typing system, so you can check whether any number, whether any variable is an instance of any other class. So this is how you can take care of your own polymorphic way of dealing with variables. So there's also the 2 plus x. I wrote here, you can write differential number 2 plus 2, 0. But there is also the reciprocal add. So the r add, that takes care of that as well. So here it is. It's the reflected addition. So if you have the reflected addition defined as well, then you can write 2 plus x. So this is technical, or perhaps not so technical. So the distinction between a function and a method. So we are now defining methods. So the methods are always belonging to a class. Is that also a method, when applied, is applied always to an object, which is referred to the self. So if we do the addition, so the x plus y is actually applying the defined add method with argument other to the object. That's the first operand. So if the reflected addition is defined, then the reflected addition is called when the first operand, when the self, is not a member of the class. Okay, so, and then it follows, so the remainder of the rules are very straightforward. So we have the subtraction here. the subtraction also deals now with the case when the order is a constant. So that's another way of saying that the g is c comma 0. Multiplying two differential numbers is defined over here. You can also see that as far as efficiency goes, that you can kind of see that the cost of differentiation and the cost of evaluating are very much related to each other here. If you're so it's actually of the same order. So the cost to differentiate is therefore proportional to the cost of evaluating. That's another way of saying it. We have the order again. The order that might not be an instance of the class. And then we have the division codified here with this rule where we override the division operator, the true division operator here. Now, of course, this assumes that the order, the value of the order, is not 0. So this is not really a robust operation here. There might be an exception handler provided, or what will happen is that the division by 0 exception will be triggered. So in that sense, it's not so strictly necessary. Dividing by a constant again, testing about the order. And then we have the main test program that will do the computation for our first illustrative example. So we have a function defined as we would define the function to evaluate any Python expression. Notice that I have here already converted my constants to 1.0, 3.0, 2.0, because in my tests I only test whether the order is a float. So again, not too extensive. If you want, you should also have tested on whether the order was of integer. But here this does it. So for a differential number 3, 1, it will compute the value of the function evaluated at 3 and also the derivative. Perhaps I should not, I have not explained this, so we are defining yet another module. So the module exports the class and the main test program. So the file that will be posted differential numbers can run as an independent program. So at the command prompt you can run this program and then the main is called. So the two lines at the bottom of this slide here are necessary if you want to use this file as a main program. If you are using only the class, or even if you are using the main, so if you import now if you would not have that if test there, but the main, then it would have the consequence that if you imported the class, the main would automatically run. And that's a behavior that you do not want. So in a Python session or in another Python program that would use the class differential number, you would like to import only the differential number, not this main. So that's what these two lines are for, which I should have explained in the lecture on object-oriented programming in Python. But this is how Python's module system works. So you can use a module as a standalone program. So it's very good practice to, even if you're not going to export the test to the main application to still include that test there. Alright, so here is the running of the test, and you see it was done with floating point arithmetic. Instead of 1.12, we have a round off there. Okay, very good. So 2 exercises now. So these are exercises meant to strengthen your ease of using Python a little bit, that make you more confident at using or that working with classes. So except of working with one variable, look at 2 variables. And another type of extension is that we can also compute the second derivative for this. If you are more ambitious, you could immediately work with any number of variables and any derivatives, but that might also require some more algorithmic thinking. So I leave it at these 2 exercises. Okay, so here is now an exercise which is very interesting for numerical analysis. So we could extend our floating point arithmetic with estimates on the round off. So if you make a round off, if you do any arithmetical operation, the relative error is on that operation is bounded by the machine precision. So for any operation that you do, you could add the machine precision. So if you have n operations here, you can estimate this, that it is the sum of all the round-offs. So the epsilon 1, epsilon 2 are the round-off errors that were computed in the computation of the arguments. So every number has an upper bound on the relative error on it. So an alternative way of working would be if you would be to do an automated operation count. So you could say, what is the cost of a number that you computed, so it has a cost associated with it, the number of arithmetical operations that were carried out on this object. This is good if you're interested in automatic cost analysis. Very early editions of MATLAB, and I think you have to be of a certain age to know this, but MATLAB used to print the number of flops after every operation. So this exercise is geared towards numerical round-off, automated round-off analysis, but you could also turn this exercise into an automated operator count. So these are more interesting, or these are alternative exercises to exercises 1 and 2. Okay, so this part, and I'm at the first half of this lecture. So the first half of this lecture is intended to expand your knowledge of Python and a little bit giving the feeling of how powerful, how useful and how powerful classes and operator overloading can be for scientific computing, for numerical computing. If you had, so coming back to this exercise again, if you have to code this up independently, then for every number that you compute with, you will have to do a lot of bookkeeping, and that would lead to error-prone coding. But instead, what you do is you have simply a tuple, and the tuple is encapsulated in the definition of the class numerical float. Okay, so now we are now at the second part of this lecture, and this part is intended if you are so it's in first part intended to give you some understanding how Python can or is used also in scientific computing. We've seen NumPy and the vectorization in NumPy. That was one approach to make it efficiently. Another way, of course, is that there is a lot of code that is compiled, not necessarily in C, but I'm using C here as what I would say as the least is the least common multiple of all languages. C is a small language and also still widely available. We can extend Python with compiled code. There are many reasons why you may want to do this. So perhaps you have prototyped an algorithm in Python and you have identified the computational bottleneck. If it is a matrix operation, if it's a linear algebra operation, then you're in luck because there is the BLAS library that you can link with, and perhaps you only have to define a wrapper function. So I will indicate then also how this goes. In a way, it requires, so this I will try to be self-contained in explaining this. So if you have never seen C, then it can be very intimidating. But if not, if so, it's also not that complicated. So first of all, what is a shared object file? It's a .so file on Linux systems, a DLL file on Windows systems, and on Mac OS you have the dylib file, so dynamically loaded libraries. So I will take a very simple example, reverting the characters in a string. I will first define a C program and compile and test this independently. Then we will write some wrapper code and build in the extension module. Actually build the shared object, and the shared object can be imported directly into Python. So here is how C works. So C works with prototypes, and in the functions you must declare your types. So when we pass a string, we pass the number of characters in the string, and we pass a sequence of characters. So the char is the type character, and the star indicates that we have what is called an array, a sequence of consecutively positions in memory. The main program works with argc and argv. We indicated that already, that you could get this also in a Python code. Both functions, so there is a main function and there is a function pass string, will return an integer. And you see the documentation strings. You also see the includes. The includes are a little bit the analog of the import. So we will do input output, we will use the standard library, and we will use a library from the string processing. So here is the swapping. So we will swap the characters in a string. So C does not have tuple assignment, so you have to work with a buffer. You have to terminate every instruction with a semicolon. And there is the indexing arithmetic that is done here. So we revert the characters in a string. We actually are changing the string itself. So the star is also the call by reference. So when we call the pass string, we actually pass a reference to a string, as we would say in Python. In the C language, we talk of an address. C is not a managed language, so we don't have garbage collection, we don't have automatic memory allocation. So that's why we need the standard library. We allocate as many characters as the user here provides. And we compute the string length of this. So the user gives the number of characters there, but then still we check on the length. So we don't want to give too many characters. If the user typed in 80 characters but then gave only 5 letters in the string, then we're going to work with those 5 letters. What if the user types 5 and then types in 80 characters? Well, that's undefined. Okay, we compile it with GCC, also available on Windows, although on Windows you do have the Studio, so there's also the community edition of this. On Mac you have Xcode. So we test our main program. See, that was it. So what we want is we want to make sure that the Python programmer can also call the function pass string. Alright, so here is the final result. So in building interfaces, there are 2 types of interfaces, and they are both illustrated here. There is the test. So the test will call the main program. So in the main program test here, the C program remains in control. So at the moment, and this is with compiled code. So this is just as efficient as executing the compiled code at the command line. So we import from our module revert strings the function test, we run it. So that's the first type of interface. In the second type of interface, the control goes to the Python user, and that's probably the interface that you really want, but that's also the interface that takes often a little bit more time to write. So we have imported the pass string, so actually it's wrong. The name is not so good here, but you can import pass string and then rename it with the as clause, as we illustrated earlier. So we pass the string, so here I can automatically compute the length. So I can do this also internally, so this function is not so efficient, not so user-friendly still, but you see that it will return the reverted string. So in the second type of interface, the control of the code is actually passed to the Python user. So there's no main program anymore. A little bit similar as you have been working most likely in the Jupyter notebook. In the Jupyter notebook, there's no more main. Okay. Now it gets a little bit more technical. So we need to do some more compiling before we can. So we cannot directly import objects. So next week we are going to go to Julia. Julia is a little bit easier on users like this. We need to compile some code with the header file of the Python system. So where is that header file located? There is the prefix. So the prefix will define where the header files are. So I will post code, and that will contain most likely or most not, perhaps not, but most likely it will. It will contain, it may contain my absolute location in the makefile. But you can get the prefix and then /include /Python and then eventually followed by the name of the version. Alright, so we have the main test here that is wrapped. So this is where the boilerplate code comes in. We define an extension module, and the extension module will contain the method test. So we have to have the test, but then preceded by this revert strings underscore. So, and what this wrapper does, it simply calls the test. The test as defined now in our main program. So wait, so there is no main program here. Importantly, the main function in the C code has been renamed into test. So in C++, you most likely can have main functions that are not called main. But here, main standalone C programs, they must have a main function defined. Here, well, could have kept with the main, but it's more appropriate to work with tests. So test is the first type of interface. And we will return an empty value, an empty string here. Then comes the wrapping itself of the pass string. So here it is called revert internally. So the method in the module will be revert, but then it will be exported as pass string anyway. You see in the middle, in the center of this definition, we have the call to pass string, but then we have the C code in between. So we have the length of the string and the reference or the S that will refer to the string on input. So the input string gets parsed by the pyarg parse tuple. So that will take the integer and the address to the string, and if correct, so if not correct, so if it does not work correctly, then it will return null. Otherwise, it will continue and call the C function, pass string. And then we will return the result value, which is what is returned. So the pass string changes the strings, changes the input string, flips all the characters, and that reference will be returned to the Python code. So after, with the build value here, we will take the variable string and turn this into an object of the type string. So I'm giving string representations. The reverting of the string here is kind of universal for passing objects too. I think I mentioned this also with the first interface that we built for the MPSolve in the first lecture of this week, lecture 6. Okay, and then comes more boilerplate code. So where you have to remember that we defined the test and the revert. But now actually the revert strings test underscore test is exported as test, and the revert strings underscore revert is exported as pass string. So and there's also a documentation string. So there's one line of documentation here. So this is all written by hand, and this works perfectly fine. To make this a little bit more automatic, you would like to have a program that takes the documentation string of the original libraries that you want to export and puts them into the boilerplate code here. But that is when you are working on really a much larger library and want to define the exporting in an automatic way. So we have the methods, then we have the module that we initialize, that we name, and at the very end we refer back to the methods. And then at the very end we have to define the initialization of the module. So there is the registration table and the initialization, as it is called. And this is by default working for Python 3. So in going from Python 2 to Python 3, there were some subtle changes that were made. But the same principle will apply. Okay, now we're almost there. So we compiled this with a GCC compiler. Now the nice thing is that you can compile this also from and build the shared object also with Python setup with a dist-utils module. So here is the code. So we define a setup, and we pass the sources to this. So if you then execute in the folder where is your sources, that will actually make the shared object. The shared object that will also be called revert strings after renaming. So that's mainly it. You can also provide extra arguments. So there are extra files other than the sources that you can provide. So you can have libraries that are already pre-compiled. So I was mentioning the very efficient basic linear algebra subroutines earlier. It could be that you have a similar library already available, already compiled. And what you then need to do is just need to write but it is all self-contained, what I try to describe here, that the main thing that you need to do is to write the C function that kind of glues the Python with the other library. Doing this with Python setup build is also very useful to see all the libraries that are linked. So you could eventually use the linking then and build your makefile if you still want to work with makefile. Okay, so this was very technical. Something very useful if you build your own modules. You may want to put them in one specific folder with all your code. If you launch your Python interpreter somewhere else in another folder, or if you're in a Jupyter notebook, your Jupyter notebook is unaware of where these modules are, you should adjust the path. So here is the example. So path is a list of folders, of absolute names of folders. That's another way to see where all the packages are that you have used to extend Python with. That could be very useful if you are using Python on a shared computer, on say a shared server, and you want to see what is installed there. So that could be one way to investigate. But here we have defined our own shared object. We have put it somewhere in a folder, say this TMP. And if we want to use the revert strings module, as I indicated earlier on an earlier slide, then you have to make sure that the Python interpreter finds your extension module. So this is a very useful construction to know. So also for any Python programmer. All right, 2 exercises. This is already more for getting a little bit more advanced programming. So the 4th exercise is asking you to try to play with installing that extension module on your computer. If you have done prior C or C++ programming before, then it might be a little bit. So I tested this on a Linux computer. On a Windows computer, it might be a little bit different, or perhaps not. The fifth exercise is on making more changes and more towards actual implemented scientific applications, where you would be passing sequences of doubles, where you would actually pass arrays. So here it might be good. I mean, either you would work with NumPy, but you might also, in your prototyping, work with the built-in array type that's provided with Python. Okay, so I have 5 minutes left for mentioning again the arithmetic application. So if you wanted to export double arithmetic to Python, why would this be useful? It would be useful for having, say, that you have a scientific application that computes with multiple doubles, and you want to export or import the results of that application into a Python session, and still verify certain things with the multiple double arithmetic. So here are the steps that would need to be done. On the next slides, I will illustrate the C interface. So the QD library is a very nice library, is self-contained and comes with a C interface. And then as the exercise illustrating the operator overloading, we would want to define the addition in the natural way, not in the functional way. Okay, so this looks very crowded, but just to indicate that in C you would represent a double as a sequence of two arrays, a sequence of two doubles. So here defined by this n between bracket 2, x between bracket 2. So we have all the numbers in C which are now arrays of length 2. A better implementation would actually have used two variables, especially if you're interested in multicore. So then the difference between the arrays that can be of any length and using separate variable names is that they can be loaded in registers. So that also makes multiple double arithmetic very suitable for shared memory parallel programming. So here you see the interface, and with the documentation I indicated the operations. So with Newton's method, that's a very good example. I can show almost all the important arithmetical operations that you want. Also the writing to string. So we can read a number from string. See here as a test I had the exact up to 32 decimal places, exact value of the square root of 2. So then here is the test program. Newton converts quadratically, illustrated very beautifully here. So this illustrates the test. So that would be the standalone test that you would be executing. So the exercise 6 is another more extensive programming exercise. Again, it involves some non-trivial operations of compiling, so downloading the QD-lib library, configuring, building, installing, and then wrapping it. So it's much more involved than what we've done, but we are doing exactly the same operations as in the reverting of the strings. Then there is a project here, but I listed as a design problem. If you look into the Campari library, then it is provides provides functions that define the arithmetical operations on any multiple double that you want. So how could you wrap this? So this would be generating code with Python. So you would probably have to figure out a way to compile the code that is generated by executing the routines that you run from the Campari library. So that realizing this would be out, well, it would make a nice project, but it's not anymore an exercise. It's more mainly intended that you think about this exercise a little bit. Okay, so this concludes the third week, and this was a very whirlwind, a too fast overview of Python, and we haven't covered everything yet. But just to give a taste of what one can do with Python, we will see more of Python, but in the next week we will flip to an alternative and scientific programming environment, that's Julia. And then for the remainder of the course we will we will alternate once with Python, once with Julia. So thank you for your attention.